Okay, we're going to take a little bit of a look at this Friedel Crafts alkylation or acylation. Chemists can get their names on reactions when they've done a lot of work and they're very useful. So Friedel Crafts alkylation, which is adding an alkyl group to a benzene ring, and acylation is the same mechanism we've looked at before, but we're making a carbon-carbon bond, which is actually very important in building bigger structures. Now, if you take your benzene ring and add an acyl group, you can have any length of acyl group. I can put this compound on here, and it will go on as expected. And you will get the C double bond O next to the ring, and then the chain that follows. In this case, we have total of 4 carbons added to the ring, and then HCl. But if I tried to do the same thing with something like a butyl group, first of all, this would be very difficult to generate because we have a primary carbocation. So what happens in the process is that we get rearrangements. So instead of an N-butyl group, we end up with a sec-butyl group, and we'll have a rearrangement of the carbocation. So if we look at the first step, again, the first step is this bond breaks and goes to the Lewis acid catalyst, and you end up, as I said, with a primary carbocation. And because that primary carbocation is not very stable, and we're probably in a very hot environment, we're going to get shifting. So this is called a hydride shift. We saw a methyl shift when we saw carbocation rearrangements earlier. So hydrogen pops over with its electrons to make a more stable secondary carbocation. And then the reaction will proceed as you expect, with the double bond going there, and you end up with your carbocation intermediate. Your sec-butyl group is attached to the ring, and 1, 2, 3, 4, and now I have not a sec-butyl group. I've ended up with an extra carbon. Get rid of it. And then a plus here. I'm just practicing my mechanism here. And then, of course, we have AlCl4 minus coming in, picking up the proton, and then regenerating the aromaticity to make the ring. It's always good to keep practicing, especially with mechanisms. So how can you put a longer chain, and by long, it means more than 2 carbons on a ring without rearrangement? Well, you're going to sort of trick it. We're going to put the carbon chain on as an acyl group with the C double bond O right next to the benzene ring. And there are a couple different reactions that we can use to take that C double bond O and reduce it all the way to a CH2. Well, when the C double bond O is right next to the ring, you just use H2 and a palladium catalyst, and that will reduce that C double bond O to a CH2. Now, this reaction will not work with any ketone. It has to be a ketone next to an aryl or an aromatic ring. So what has just happened is that we've been able to put our new carbon on and then reduce it to an alkyl group. And you might be wondering, how come the double bonds in the ring don't get reduced? Well, in order to reduce a benzene ring, since benzene rings are so stable, you have to use a platinum catalyst, and you have to use high pressure of hydrogen to make sure, that's a high pressure of hydrogen to make sure all those double bonds are reduced. So it's not going to reduce the double bond. It's only going to reduce the C double bond O. And we will use this when we get to synthesis problems, because what we've done is taken a group with a C double bond O and changed it to a group with a CH2. And these two groups direct the next electrophile differently.